show you some cool tricks with magnets, but first, let's talk about how a magnet actually works. I've got some ping pong balls in front of me here, and let's say they represent the nucleus of an atom. So we've got protons and neutrons all clumped together, and all about that nucleus are these electrons whizzing about. Each electron carries with it a negative electric charge, and any moving electric charge creates a magnetic field. So you might think all atoms have a magnetic field around it with the electrons moving about. However, in most atoms, the electrons come in pairs, and the way this pair of electrons move about each other cancels out any sort of magnetic field. Some atoms, however, contain an unpaired electron, say iron. And this does create a magnetic field around that atom, so it's a tiny magnet on an atomic scale. And as you get more and more of these atoms together, it creates a stronger and stronger magnetic field. So you collect thousands and thousands or millions and millions of these atoms, and it creates what's called domain. And that would be all the magnetic fields line up the same direction. So north and south are all pointing the same way within this small clump of metal. Say, for example, that I've got this piece of steel. And within this piece of steel, there are a whole bunch of domains, maybe thousands and thousands of domains, and each one on the microscopic level. Each domain has the north and south pointing the same direction, so it is its own little magnet. However, because there are tons of domains in here, each one pointing in a random direction, north and south are pointing all over the place, any sort of magnetic field cancels out. So, say for example, I get this screwdriver pen. This thing cannot pick it up. It is, by itself, not magnetic. Now, let's say I take some sort of external magnetic field, like this rather large permanent magnet. When I attach it to the piece of steel, all of the domains within that piece of steel suddenly line up to match that of the magnet, which means that this piece of steel has become its own magnet. When I remove the magnet from the piece of steel, all of the domains in that piece of steel go back to their original orientation, which means all over the place. So this piece of steel is not magnetic anymore. Some metals can be made to stay as a permanent magnet. For example, I have this piece of neodymium iron boron. By itself, it had really no magnetic field to begin with, but a strong magnetic field was applied to this. All the domains lined up, so north and south were facing in the same direction. And once the magnetic field was removed, all those domains stayed as a property of this metal, which creates my permanent magnet here. I mentioned earlier that a moving electric charge creates a magnetic field. The reverse is also true. A moving magnetic field can generate an electric current in something like, say, a wire. What I've got here is a whole bunch of wires wound around a spool. And when I drop this magnet through, as the magnetic field moves through those wires, it's going to generate an electric current. And this current is going to flow to my electronics here, and there's going to be enough energy to light this LED. Let's see it in action. We can see the results of these electric currents being generated with this LED lighting up. Let's see it again. We can see this property in action in something like generators, which are used to create electricity for your homes. Take something like coal. We can use that to boil water. The steam is then sent through a bunch of turbines that turn some wires in something, say, like magnets. These turning wires generate electricity because they're going through magnetic fields. This electricity is then sent out on the grid to your homes. Now, we've been talking about how a moving electric charge can create a magnetic field, and how we can take a moving magnetic field to create electricity. Here's a fun fact. If I have a moving electric charge, or say current, that current is creating its own magnetic field. That magnetic field will always try to repel the original magnetic field that created it. And we can see that in action. I've got this copper pipe, say something you can buy from the hardware store. And if I drop any non-magnetic object through it, it falls straight through. Let's see it again. Now, if I take something magnetic, like my permanent magnet here, and drop it through, what happens? What's going on? As the magnet moves through the copper pipe, it's generating a bunch of currents within the copper pipe because it's a moving magnetic field. These currents are creating a magnetic field, and that magnetic field will try to repel the magnet no matter the direction of the magnet. Let's see it again. This is a property known as Lenz's law. I've shown you how a moving magnetic field can be used to generate electricity, and how an electric current can be used to generate a magnetic field. The thing to remember here is that magnetism and electricity are interrelated. They always go hand in hand. Now, if you'll excuse me, I've got some gravity to defy.